let's talk about second order linear homogeneous with constant coefficients. Now, pretty much everything we do today will apply to nth order, any order, but it's easier if we start with second order. So all of this would apply to third order, fourth order, and so forth. But we do need it to be linear homogeneous, meaning equal 0 with constant coefficients. So I don't know, maybe y double prime minus 6y prime, what am I, 8, plus 8y equals 0. So it's linear. All of my y's are linear functions of y. They're to the first power. There's no cosine of y or e to the y. Homogeneous because it's set equal to 0. Constant coefficients because these guys in front of all the versions of y are just numbers. Then we assume our solution is of this form, e to the lambda x. Or when I learned this, we used s up there, e to the sx. My s's look too much like 5s, so I tend to not use s, but that's fine. Some people use k, e to the kx. Perfectly fine. I don't care what parameter you use there. So we assume we have a solution that looks like this. So let's plug it in and see what we get. So y prime would be lambda e to the lambda x. Y double prime would be lambda squared e to the lambda x. So plugging all that in, we'll get lambda squared 6 lambda e to the lambda. And then 8 times the original equals 0. Now this is supposed to equal 0 identically. E to the lambda x never equals 0. I could factor that out. That thing never equals 0. So the only way this can equal 0 is if this quadratic in lambda equals 0. We call this the characteristic polynomial. And notice it literally looks exactly like the original DE. It's exactly the same as the DE, just whatever order of derivative I have becomes my power. I had a 1 here, 1. Second order, second power. First derivative, first power. No derivative, no power. Keep in mind that y is the 0 order derivative of 1. So that's going to happen every time. Like we'll get to the point that we'll skip doing all this work and we'll just go straight from here to here. Because it's going to look like that every single time. So we just want to solve this for lambda. Well, that factors, that's lambda minus 4, lambda minus 2 equals 0. So we get 2 solutions. So that means the possibilities that we said here for y are maybe y1 equals e to the 4x and y2 is e to the 2x. Now remember last time we said the order tells us how many linearly independent solutions we need. The general solution here will have 2 linearly independent functions. E to a different power is linearly independent. I don't need to do the Wronskian. I could. Like I do a bunch of examples with Wronskians. You can check. The Wronskian of these two is 0. These are linearly independent. So then my general solution will be y equals some constant times y1 plus some other constant times y2. So C1 e to the 4x plus C2 e to the 2x. Put it over here. And that's the way this is going to work every time. If we have a second order, we're going to get a quadratic. We're going to solve that quadratic. And as long as we get two unique solutions, two real unique solutions, we're done. We'll write it out like this. What happens when we get a repeated solution? Well, then we got to do a little bit more work. And what happens when we get complex solutions to that quadratic? Again, that's a little more work. Okay, let's do one with a repeated solution. Let's say we have y double prime minus 6y prime plus 9y equals 0. Okay, so I'll write it out again, but really we could just skip to the characteristic polynomial. We assume y equals e to the lambda x. So y prime is a lambda e to the lambda x, and y double prime is a lambda squared. Plugging everything in. Factoring out the e to the lambda x, which can never equal 0, we get lambda squared minus 6 lambda plus 9 equals 0, which factors lambda minus 3 squared. We only get one repeated solution. That's a perfect square trinomial. So let's write that out. So we know we need two linearly independent solutions to build our general solution because it was second order. If it were 10th order, we would need to find 10 solutions. We know y1 is going to be e to the 3x. Now we got to find another one. And like this is one of those times where I know what to do because my professor told me, and now I'm going to tell you what to do. I would not expect you to come up with this on your own. I don't know if I would have. Our second one, we're going to take that one and just tack on an extra x. When you have a repeated solution, tack on an extra x. If this had been fourth order and we had gotten, I don't know, maybe like this to the fourth power, so it was repeated 4 times, then we would just keep tacking on extra x's. We would have y3 is x squared, and y4 would be x cubed times e to the 3x. Just keep tacking on extra x's until you get everything you need. Now, let's go through the work and prove that these are linearly independent. And I did that in one of the videos, I think. I don't know if we need to do that. You can check that the Wronskian of those two is in fact 0. That might even be one of the test questions on the next test. I want to prove that this is a solution. So first, let's write down here, I claim that my general solution will be C1 e to the 3x plus C2 x e to the 3x. Okay, so I wish I hadn't erased my DE. What was it? That. And I claim y equals x e to the 3x is a solution. Let's check that. So y prime, I have to product rule that, will be e to the 3x plus 3x e to the 3x. Y double prime will be 3 e to the 3x plus 3 e to the 3x, derivative of the first times the second, plus 9x e to the 3x. Let's check that and make sure that was right. Derivative of the first times the second, derivative of the second, leave the first alone. Okay, so let's plug all that in there. Oh, well, let's combine those together. These are like terms. And then 6 times this one, I'm going to go ahead and distribute. Minus 18. Plus 9 times the original. Those cancel. Those all cancel. It does, in fact, equal 0. So yes, that is another solution. Okay, what about when we get complex solutions? Okay, well, there's a lot of math that goes into that. I'm not going to walk you through all of the math. You can look here on pause. And he walks through how we derive all these formulas using Euler's formula for exponentials and so forth. I'm just going to tell you what to do. Here, let's just walk through one of his examples. Okay, so here's our original DE. We get this characteristic polynomial. Notice it's really just same coefficients. And here are the roots. 2 plus or minus square root of 5i. Just use quadratic formula to get that. Within our general solution is going to look like this, where the power in the exponential is our a. So here are our roots, lambda plus or minus, think a plus or minus bi. Whatever is the a goes in the power of your exponentials. Whatever the b is, the imaginary part, will be part of your argument of your sines and cosines. So our general solution will be a mixture of exponentials and sines and cosines. So look, the 2 came there. The square root of 5 is in the cosine and the sine. And that's just something you just gotta learn. Again, here's all the math up here for how we know to do that. But I don't really find this instructive going through all the math. It's just using Euler's formula.